Okay, welcome back, everybody. Derek, Mr. Bloom, thank you for sharing that Discord. Hopefully you guys can get together and help each other out. Again, I'm available here, but I've not heard too much chatter as far as email from my end. So anyway, I'm still here. So why? What, tomorrow we open up the first exam, which consists of chapters 1 through 3. We're in slide 13 today. We'll get that knocked out. And any other questions, we can do any other or answer any other questions concerning the other chapters. Otherwise, I'll just continue with chapter 4. Okay. All right. Well, let me get everybody in here. That's good. All right. So, okay. So let's jump into chapter 3, knock it out, and then we'll go from there. Okay. All right. We were on slide 13. Okay. And we had just finished talking about doing examples of conversion vectors, basically using a process factor label method or dimensional analysis. There's a variety of different names out there that utilize that. And it's simply put, to me, I just, it's a method where you keep track of the units and you set the problems up with conversion factors. All these conversion factors, if you recall, are ratios. So one of them, like 1 inch is equal to 2.54, 1 inch equal to 2.54 centimeters. That is a ratio where I can put the inch in the numerator or invert the whole thing. Which one I use depends on the question asked and what units I'm striving for at the end, okay? So, and that technique we're gonna utilize when we start getting into chemistry and we start doing calculations with respect to chemical reactions. And that's down the road. So, a master that technique, I can tell you, I've already seen examples where people have used alternative methods. I couldn't quite follow what they were doing. All I can say is at the end, the answer was incorrect for some of the questions I've seen. So I will give credit if I have a multiple step question where it says show your work and you're going to need 2 or 3 equations. Obviously, I break up that answer with X amount of points. Normally, the point itself is just worth 1 point. It could be 5 point overall. And the other 4 points are broken up to give you credit for how you set the problem up and you set it up properly. Point being is some people have in the past presented an answer, a 5-point answer, but they only get 1 point. Yeah, they were correct, okay? And the other aspect of that too is maybe they wrote a simple answer, but the answer is incorrect. Again, I couldn't give them any points there because I had no idea where they went wrong. I've had questions where they presented they showed their work, and maybe for a grammatical reason, they pushed the wrong button. They got a wrong number, but they showed their work. And guess what? They showed their work. They got 4 points. Obviously, they didn't get the 1 point for the answer, but the 4 points because showing your work was shown. Okay. So keep that in mind if you ever have to show your work or asked to show your work. All right. So we're going to get into volume by displacement. This is pretty self-explanatory. I know you're well aware of this, okay? Simply because let's say you're jumping a jacuzzi, you jump in the tub, you jump in anything that contains a body of water, you get in there, what happens to the volume of that container? That volume goes up. And so if you knew the exact volume of, let's say, of the water in a jacuzzi, and then you go in and completely immerse yourself and you have someone mark with that new volume, that difference of volume of where it ended minus where it started is the volume that you displaced. Now you may, why do I need to know this? Simply because density, we kind of introduced density a while back, kind of real briefly. Density is a ratio, is a physical property of matter. It's a ratio of mass of that matter divided by the volume of that it has. Now, when a chunk of matter has a nice uniform shape, rectangular, square shape, we can readily measure its volume, length, width, height, okay? Length times width times height gives us the volume. That's where we get cubic centimeters. 1 centimeter times 1 centimeter times 1 centimeter gives us 1 cubic centimeter, which happens to be equivalent to 1 milliliter. So 1,000 cubic centimeters, it would be equal to 1,000 milliliters, which is equal to 1 liter. Okay. So with that said, the mass of any chunk of material matter is straightforward. We just simply weigh it. So now you have the mass, you have the volume, and now you have a physical property for that material, which is the density. Okay. So in this example here, this is a diamond was placed in a graduated cylinder. Nothing more. Graduated cylinder is nothing more than a cylinder with marks that gives us volume measurement, so we can measure the volume. In the beginning of that cylinder, graduated cylinder contains 20 milliliters of water. The diamond is placed into the cylinder, and the volume, obviously, like us jumping in a jacuzzi, goes up because it displaced an X amount of volume. And the new volume reading now is 34.7. A key point here, that is not the volume of the diamond, okay? That is the total volume of the original 20 milliliters that was in there to begin with, and the volume of the that the diamond displays. Okay, the error I always see is that yes, you measure the weight, you got that, no problem, right? But then instead of dividing by the actual volume of the diamond, one divides by 34.7, and that's totally incorrect. We're interested in the volume of that diamond. Okay, and so simply put, we have to subtract the volume, the final volume, minus the initial volume. And that difference is the volume of, in this case, the diamond. And this is true for anything that you do that has irregular shape. Yeah, that's the best way to calculate the density. Okay. All right. So we'll get back to that. Wow. To calculate the density of any rectangular box or square, like I mentioned, is a straightforward measurement of length, width times height. Okay, and so volume, length times width times height. If you are measuring, if you got to do this and you're going to, calculate the volume, make sure you're using like terms. Let's say, for whatever reason, one of these numbers is in millimeters. Well, that would be incorrect to multiply all three numbers and assume it's cubic centimeters, right? And so we're looking for volume. We're going to make sure that all the units are the same, be it English units or metric units. In this case, they are, because it's 24 centimeters times 11 centimeters times 16 centimeters. All three numbers have 2 sig figs, so our answer should have no more than 2 sig figs, okay? And that turns out to be 4,200 cubic centimeters. Don't forget your units. All right. And that is the volume for this particular box, is as we measured it out. We could also do it by displacement. If we had a big enough container with the known volume, we could put that rectangular box and measure its displaced volume, and we should get closer. We should come up with 4,200 cubic centimeters or milliliters, right? Because we know that 1 milliliter is equal to 1 cubic centimeter, 1 cc. Which brings us to this ratio we've been talking about, which is called density, okay? And that is simply a ratio of the mass divided by the volume. So the units of density are mass units over volume units. In general, the most common unit utilized is the one in the center here, where we got grams per milliliter, okay? But you will see them, you'll see things like kilograms per cubic meters, okay? So those are just simply the density units, and it is a ratio. So therefore, we can take that ratio like we worked in the units before and invert it and say, you know, given the density of a material, we can calculate its volume or we can calculate its mass, okay? By simply playing with the ratio and putting it properly, okay? Density is nothing more than just the space that matter is given. Now, it is a ratio, and I want you to think about this for a second. Let's take a loaf of bread, rectangular loaf of bread that you get from the grocery store. And you could measure, obviously, its mass, okay? You measure its mass, and you can measure its volume. We can get a ruler or tape measure and measure length, width, and height. It's a rectangle, okay? So that gives us a pretty good volume. And so we take that volume and we divide it by we take the mass of that loaf of bread and we divide it by the volume we calculate. Now, let's say you had, like I did, a bunch of boys and you went to a grocery store and they took that loaf of bread and they squished it, okay? Now, let me ask you a question. Would the density of that loaf of bread change or would it remain the same? What do you guys think? Okay, I got remain the same. We got some, okay, remain the same. Okay, so far. If that question was worth 5 points, it would be negative 5 points. Okay, let me explain. Okay. Let's say that loaf of bread, for argument cases, weighed 100 grams, okay? And so D is equal to 100 grams, all right? And then we measured it, and maybe it's 10 centimeters by 10 centimeters by whatever, let's just say we ended up with, so that's grams, 100 grams, and we measured it and we ended up with 1,000 cubic centimeters. So we could say that it is 100 milliliters, correct? All right, and so the density for this loaf of bread, this theoretical loaf of bread, would be what? What do we got? .01 maybe? Okay, 1/10, okay, 0.01, 1 gram per 10 meals. And those all would be legitimate answers. Normally, the way that answer is presented is simply just do the math, 100 divided by 1,000, and that it corresponds to 0.01 grams per milliliter, okay? And Canvas would understand that answer as 0.01. The other answers are not incorrect. It's just that Canvas is going to assume that you did the measure out. Okay, you actually did the calculation. Carried it through, I should say. Now, so your kids took that loaf of bread and they squished it down to about 1/4 its dimension now. And so now it's still 100 grams. Okay. It's still 100 grams, but what's happened to the volume? Okay, so this is density I, initial. This is density final of that loaf of bread. It's still 100 grams, but what's happened to its volume? It's because they squished it, it's got a new volume. And just for argument's sake, it went from 1,000 milliliters, now it's 100 milliliters. What's happened to the density? What is the new density now? Exactly, Derek. You decrease the volume, so therefore that ratio goes up. And so now your new density is 1 gram per milliliter, okay? Simply because that volume got smaller. And if for whatever reason you were able to expand the volume, then what happens, the denominator gets bigger, right? So that number becomes even smaller. Okay, so that density is governed by, the mass is not going to change. It is what it is, okay? The mass is always be the same, whatever, any piece of material, but the volume, depending on what it is, what material it is, if it's a solid, it can change. Excuse me, it's a solid, I meant to say, it cannot change because the solid compressed. The liquids, not so much. Like, let me go back to the solid. It depends on the material, okay? You heard the old line where, you know, what weighs more, a ton of feathers or a ton of steel? Well, obviously, they're both the same, right? Ton is a ton regardless of what it is. But if you ask the question, who has a higher density, a ton of steel or a ton of feathers? What do you think? Ton is a ton. However, when we talk about density, who's going to have the greater density, the feather or the steel? Okay, so far we got the steel, okay, but before you answer, think about the bread and what happened to the bread. Okay, and then think about feathers. Think about your pillow. Can't you not squish that a little bit? So the answer would be, it depends. It depends, again, the steel is going to have a constant density because it's a solid and we can't compress that steel anymore. The feathers, on the other hand, you know, yeah, we can put them in the container and measure its density and say, okay, that's our density. However, we can take those feathers, there's a lot of air in there, we can compress them and end up in the same scenario where if we compress enough, we could theoretically make its density greater. Yeah, well, technically we need a volume to answer that, and that would be correct, okay? That would be correct. But the idea here was to think, well, yeah, okay, I got the volume, but what can I do different with the volume of the steel versus the volume of feathers? And that's one reason density, that ratio, that ice expands. And if you ever lived in cold weather, you risk busting your pipes because water on freezing, it's a weird, not weird, but it's an interesting property of water, is that when water freezes, it expands. And therefore that ratio changes, okay? And therefore the density changes, and therefore ice floats because its density now is much less than the original water, which is about 1 gram per milliliter at 25 degrees. Okay, let us move on. So we know common sense tells us which state of the matter is the most dense. Well, it's solid, obviously, simply because we cannot do anything with that volume. It's already pretty compressed. We can't compress them anymore. Okay. The state of matter which would be least dense are the gases, and you can see here some density values, that the density of air, how small that is as compared to, say, density of gold at about 19 grams per cubic centimeter or milliliter. Most metals are pretty high like that. Okay. And then the density of water is our little kind of benchmark. If a density is greater than 1, normally what happens if that material is not soluble in water and it's a solid, it will drop like a rock and sink in water. If it's less than 1, if they don't mix with water, it will float on top of water. Okay. Some liquids, organic compounds, material, have a density that's higher than water and do not mix with water, and therefore will be below water. We get 2 layers, one layer of an aqueous layer and one kind of oil-like layer. Look at Italian dressing. Okay. Italian dressing is a good example of oil and water, and you get 2 different layers. All right, so with respect to density calculations, we have a couple of types, 3 types. Yeah, type 2 is 2 types of type 2. One type is the straightforward, you're given the mass, you're given the volume, boom, do the math, keep track of your sig figs, you got its density, you've calculated that, okay? Second type is this, you are given the density of a material, and with that information, that ratio, you can calculate either the mass or the volume of that material, okay? Depending on how you set that problem up. For example, chloroform, which is a liquid, it's an organic solvent. Back in the day, when people would be knocked out to get an operation, that's what they did. They would give you a little sniff of chloroform and you're out like a light, okay? It has a density of 1.48 grams per milliliter, okay? Grams per milliliter, which means chloroform having the property that it has does not mix with water. We have 2 layers. In fact, here, if we had 2 layers, we would see that chloroform would be down in the bottom of water, which would be floating on top, okay? Why? Because that's higher density, it's more dense than water. Now, that particular ratio, and it's a measurement, keep that in mind, for all densities are measurements and therefore could play a factor with respect to sig figs at the end of the day when you do your calculation, okay? But that ratio, like any ratio we work with, can be written with grams in the numerator or grams in the denominator, okay? So 1.48 grams divided by 1 milliliter or 1 milliliter divided by 1.48 grams. Which one we utilize depends on the question and the units that we're searching. Obviously, you can see that if I'm looking at the end for units of grams, then I'm going to be using this one here because the conversion factor has grams in the numerator and the milliliter is going to cancel. If I'm looking for milliliters, obviously, this is the one I'm using. Now, the other aspect about these conversion tables, I've seen it with my other classes, is students have taken these conversion factors and inverted them, or they mistakenly written them. Let's say, for example, we're going to rewrite this one here, and they write 1.48 milliliters per 1 gram. You see what they did? Yes, the units are correct, but the number was written in the wrong position. So think about that carefully when you set up your system here. Yeah, first of all, what does that make sense? 1 gram per 1.48 milliliters. That's not the case. Okay, so check your numbers. Others have taken the inverse of this number, 1 over 4.84, and written it there. And that's fine, but sometimes I've seen it in numerous occasions that number you just took the inverse in, as I wrote here, is placed in the wrong position and again takes you to the wrong answer. So my recommendation with these conversion factors, whatever they may be, leave them wherever they are and just put them either in the numerator or the denominator, wherever they need to be, okay? All right, so we got chloroform, 1.48 grams per milliliter. All right, we're gonna come back to this one here and do some examples, but here we're gonna do a simple, straightforward calculation of density. Here you got a necklace that has a mass of 484.56 grams, and it has been determined it has a volume of 25.64 milliliters. More likely to use the displacement method for that. Okay, so that is the equation for density, and therefore we plug the numbers in and keep track of your sig figs. You can see that the numerator has 5 sig figs. The denominator is least accurate. It has 4 sig figs. So your answer has to be written with 4 sig figs. And the density of that necklace is 18.90 grams per milliliter. Okay. So you think about that for density. That means that if I had 1 milliliter of that necklace, guess what? It has a weight of 18.90 grams. Okay. And if I have 25.64 milliliters of that necklace, I have 484.56 grams. That's how much it weighs. All right, so now we go back to the chloroform. So chloroform here is 1.48 given to you. They're asking you the question is, how many grams would the 17.5 milliliters of chloroform weigh or have a mass? Okay, so basically is this: you're in the lab, you take the chloroform, you take a graduated cylinder, and you measure out a volume of 17.5 milliliters. Now, we need to know the weight. For whatever reason, you're going to use in the calculation. And normally when you do a calculation of chemical reactions, you need these units in grams. Okay, so we need to take that 17.5 milliliters and convert it to grams without having to weigh it. Yes, of course, you can go directly to the balance and take out 17.5 milliliters and weigh it. But why do that when you know the density? Okay, and so here, I set up my equation. I'm given 17.5 milliliters. That is what I'm given. Okay. Obviously, I'm going to have my conversion factor, my chloroform, and the units I'm looking for are in grams. So that's what I write down, so I know, keep track of where I'm going. That means that if I'm given 7 milliliters, units of milliliters, then I got milliliters in the denominator. They have to be there because I want those to cancel, and grams are in the numerator. So therefore, now I just simply plug in that number, okay? And I set the problem up correctly, unit-wise. Simply now, it's a matter of you plugging in that number into your calculator and getting the answer, keeping track of your sig figs, okay? In both cases, the density is a measurement. The volume given is a measurement, so they could be factors. Both of them could be a factor in the final sig figs. Fortunately, they both have 3 sig figs, so an answer should have no more than 3 sig figs. Okay, so 25.9 grams. You think about the answer now. What is that telling you? It is telling you that if you were 2 things, if I take 17.5 milliliters and I measure that volume out, I don't have to go out to the balance or weigh it. I just use the density, and it has a weight of 25.9 grams, okay? By the same token, I can reverse that and say, for whatever reason, I went to the balance and I weigh out 25.9 grams. What does that tell me? Well, that tells me that the volume of what I weighed out is 17.5 milliliters, okay? I could be in a position where I gotta know one or the other. So knowing density, I can calculate that. All right, next scenario is here. How many milliliters? So I always mark what units I'm looking for because that helps me keep track of where I need to go and how I'm going to set the problem up. What is the volume? Okay, how many milliliters would 0.0735 grams of chloroform occupy? So in this scenario, we are weighing out a very small amount of chloroform. Okay, Obviously, I need my conversion factor here. I need it so grams is in the denominator and milliliters in the numerator. Okay. And so now I have 1.48 in the denominator and 1 on top. Check my units. And I've set that up properly. So now I take 0.0735 divided by 1.48. I got 3 sig figs here. Okay. 3 sig figs in density. So my answer again would be in 3 sig figs format. Right. So that would be a 0.0497. So again, in this scenario, we don't have a lot of tools. Well, we do have tools that can measure that small volume, but not with that accuracy. Okay, so, but we do have balances that we can weigh out 0.0735 grams. And if needed, we can calculate its volume that it occupies for whatever reason. And it has a volume of 0.0497 milliliters. Okay, so these are 3 examples of how to do density calculations. One, the direct method, you give them the mass, you give them the volume, calculate the density. Second of all, given the density of whatever material, you can calculate either the volume or the mass of that material. Okay. All right. So that kind of, any questions about this density? Because we're going to go a little bit into energy. We're going to touch on more of it later down the road, but we're going to kind of introduce it. Again, a lot of we talk about is, you know, you're like, hey, I know this. Okay. Well, yeah, self-explanatory. You're familiar with, it's not foreign. Okay. And that's the next topic here. Okay. Because if you think about it, we got hot molecules, whatever they may be. Maybe you're boiling water. Okay, they're going to move fast. You know, you ever boil water? Of course, more likely you have, hopefully. Okay, you take a pot of water, you stick it in the oven, the top of the stove, turn that on, and that water starts to move, right? Because the energy of the burner is being transferred to the water. That water molecules start to move around, and you've got bubbling action going on. And then if you have enough energy into the system, you're going to boil that water and change its physical state from the liquid to the vapor phase, right? It's all about energy. So hot molecules obviously move fast because they have high energy. That's the reason. Hey, you're at the beach, 110 degrees out there, all right? You're walking barefoot in the sand. Do you think you're going to nonchalant walk on that hot sand? More likely not, unless you got some calluses on that feet, right? You're going to take off because why? The sand's hot, you know, it's going to burn your feet, you know, so you're going to move, all right? And the converse is true, that cold molecules are going to slow down, okay? They're going to move slower. Why? Because they're going to have lower energy. And that's, again, what's happening with condensation. You got the hot air molecules out here in the atmosphere. They're moving around with high energy. They come and they meet your glass is ice, filled with ice. So that's lower energy than where they're coming from. So that energy, which is high, gets transferred to the low. Okay, remember that nature transfers energy from high to low. It's always downhill. Can you go uphill? Yes, you can do that, but it takes energy to get you up the hill. Makes sense, right? Climb a hill, it takes energy to climb that hill. How about rolling down? Not so much, right? You start rolling down, you trip, your gravity takes care of that for you. It's not a lot of energy exerted unless you know, well, I guess it is if you're trying to stop that roll off that mountain. So temperature, obviously, as you know, is a measure. We measure temperature with the thermometer. Haven't seen your meeting. Thermometer. Excuse me. Okay. Now here's the deal here. You're not measuring energy. The energy of the system is either going to pick it up, kick the temperature of the system. Okay, if you put more energy into the system, you're going to raise the temperature. It's okay. You're measuring that by using the thermometer because the temperature goes up. All right, we have three types of scales. We're all familiar with F, Fahrenheit, and Celsius, obviously, right? The new one that you may not be familiar with is K, all uppercase K, named after Lord Kelvin, a English scientist. All right, now the thing is about the Fahrenheit and the Celsius scales, they will go to infinity with respect to their number up above, all the way above 100. Here we got, let me say, this is boiling point of water. So 100 degrees Celsius is 212 Fahrenheit. 0 degrees Celsius is 32 freezing Fahrenheit. Both of these scales go to infinity, to wherever the number may be, okay? Kelvin does not. Kelvin stops at 0. And that is where what we call absolute 0. That is the state, theoretically, that all matter essentially stops. Even as we drop in temperature, molecules are moving, even though, even in the chunk of ice, we would think the molecules would not move. They're moving there. They just happen to move not so much as compared to as the molecules of water were in gas or liquid, but they are vibrating and they are moving. And if we ever bring something down to 0 Kelvin, that's where the theoretically is taught that even that movement stops. We haven't reached that yet. We come close, but close, but no cigar, okay? There is some interesting phenomena occurring down at the low temperature, like a whole new science down there. But anyway, we have three different scales: Fahrenheit, Celsius, and Kelvin. Now, we're going to be talking about converting from one to the other. To go from Kelvin, let's say we are in Celsius, we can go directly to Kelvin by simply adding 273. So you add 273 to your Celsius temperature and you got Kelvin. And don't forget the letter K, the units, okay? We cannot go directly from Fahrenheit to Kelvin because Fahrenheit is English, obviously. So if we start at Fahrenheit and we need Kelvin, we need to convert the Fahrenheit to Celsius, and then from the Celsius, add the 273 and we're there. And the same is true vice versa. If we're at Kelvin, and for whatever reason we had to go to Fahrenheit, we had to go from Kelvin to Celsius, and then subtracting 273, and then convert from Celsius to Fahrenheit. Now, do you have to memorize the equations? No, you don't, okay? Just they're given to you here, but they're also in your shapes table, okay? And so if you have Fahrenheit, and you need to get to Celsius, subtract 32 from Celsius, and then divide by 1.8. I did have one student did have a problem yesterday from a Thursday class. They could not get the answer correctly. They kept typing the number. It turns out for her calculator, she needed to type in Fahrenheit minus 32, then hit the equal, and then hit the divide by 1.8. And check that number out, see if that's the case for your calculator. Some calculators don't understand the function of doing the mathematics correctly. So make sure yours is not one of them. And like I said, you can't go wrong by hitting the equal after each mathematical function you tell it to do. That would always, regardless of what calculator, always give you the correct answer. So Celsius, take Fahrenheit, subtract 32, divide by 1.8. If you want to get a ballpark estimate, not for your assignments, but just a ballpark estimate, take the Fahrenheit, subtract 32, divide by 2, take half of that. That's a ballpark for Celsius, but don't use that for the actual calculations in Canvas. With respect to Fahrenheit, if you have Celsius, again, here you take Celsius, multiply by 1.8. You may need to hit equal and then add 32. Depends on your calculator. Okay? Try it. And then finally for Kelvin, simply take Celsius and add 273. So Phoenix, for example, can get up to 115. See if you try the calculation, see if you come up with 46 Celsius and 319 Kelvin. Okay. All right, any questions about that? Pretty straightforward. The equations are given to you. You don't have to memorize them. They're there. All right, a little bit back to energy and heat. We have two beakers here. Diagrams, obviously. It looks like there's a thermometer in there in red, and it's measuring 100 degrees Fahrenheit. Both of them are. So the question number one, just to me when I first saw this, I mean, that makes sense, but okay. Which of these two beakers has the higher temperature? Well, they both depict 100 degrees Fahrenheit, okay? No big deal. Now, the difference is this. Which one has the greater amount of heat energy? Okay, A or B? What do you guys think? They both have the same temperature, but when you see the word heat, always take it with heat/energy. So would A or B have A would have the greater amount of heat. And that is correct simply because you have more matter in A, okay? Now, obviously, both of them are at the same temperature. And if I were to, you were to try this at home, you can see for yourself. I got a small little pot of water. I put it in the stove to boil it. I got a big pot, you know, a big old pot you can make spaghetti with water. You got about, you know, a gallon or two of water. Put that in the pot. Point number one. Note to see which one is going to boil the quickest. Obviously, the small pot is going to start boiling much quicker than the big pot. Why? Because there's more matter, more material in the big pot. And all the energy we put into the system is being used in the big pot to pull the molecules, the water molecules, away from each other, okay? And that's a lot of molecules, so it's going to take a lot of energy. Eventually, when the big pot is boiling, they're both boiling at the same temperature. But the smaller one having less matter, if I had to have something spill on me, I'd rather have that little one spill. I wouldn't have either one spill on me, but I'd rather have that little one spill on me. Why? Because that big one has a lot of energy and cause a lot more damage than that little one. Not that the little one wouldn't cause any damage, but I'd rather take the little one. And so there's a phenomenon that you may have heard or hear about. It's called El Nino. Anybody know? There's two of them, El Nino and La Nina. Anybody know what that is? You ever heard of that? Maybe in the weather report, they talk about, yes, lots of waters, lots of storm. And what it is a body of water out there in the Pacific, a large body of water. And there's a temperature differential in that large body of water by a few degrees, not a lot. And that's enough because of that energy involved there to actually affect the weather of the world. You know, and you would think that it's such a few degrees, but energy-wise, it's a large body of water, and that can affect the weather, you know, way down the road there. Okay. Has more heat. This is pretty self-explanatory. We just talked about that. All right, heat transfer, always from high to low, okay? And this, again, another example, this here, they talk about a cookie. Obviously, you've got a cookie, you're cooking it, it's in the oven, it's hot, you take it out, put it, you grab it, you know, what's gonna happen? Well, who loses? The heat, the cookie does, right? Because that heat, the cookie is a higher energy level than your hand. And as you grab that cookie and it's hot, it's gonna burn you because it's transferred that energy from high to your hand, which is a lower temperature. And a good example of this phenomena would be taking a nice warm shower in the morning, hot shower. All right, you're in the shower stall. The hot water's going, very comfortable. Okay, you're done. You shut it off. You open the door, shower door. You step outside to dry out. What happens? You get cold, right? Think about this. You are at a higher temperature, energy-wise, than outside the shower. And the environment outside the shower is at a lower temperature. So the energy that you have, which is higher, gets transferred to the environment outside the shower. And so you get cold again. So what do? You jump back into the shower, but now you are lower temperature than the shower, within a reasonable time here. Okay, so now the shower inside the shower that you have just used is warming you back up, because now its energy is being transferred from the inside the shower back to you. Okay, eventually everybody is going to get to whatever temperature the environment is, the ambient temperature. If it's room temperature, 25 degrees. If you're still dealing with, being in North Pole, your temperature, you're all nice and warm, and you go outside, your temperature eventually, if you're not careful, will get down to freezing. Okay, it's a matter of always going from high to low. And yes, you can go from low to high, which is what your refrigerator and freezer does, but it takes energy into the system to do that, okay, to reverse the process. And so here, pretty self-explanatory, you got a piece of metal, it's placed in the freezer, okay, and then the metal is then taken out and put into a bucket of hot water. So the question here says, does the temperature of the metal increase, decrease, or stay the same? What do you think? You got a frozen piece of metal, put it into the hot bucket. What happens to the temperature of the metal? What do you guys think? Does it stay the same? Does it increase, or any change at all? It increases, exactly. Okay, because it's taking the energy from the hot water and is being transferred to the metal. So if you want a quick way to warm your coffee up, cool your coffee up, not warm it up, excuse me, to cool it off, put in a cold spoon or two inside your hot coffee. That metal will actually pick up, that cold spoon will pick up some of that heat, okay? And eventually temperature will decrease. Everybody will eventually get into equilibrium to whatever environment they're in, okay? Everybody will eventually get to room temperature. You don't believe me? Take a cup of hot coffee, cocoa, whatever. Let it sit there for about 30 minutes. Tell me what happens. Is it still hot after about 30 minutes? No, not at all, right? Because that energy goes away and it dissipates into the environment until it equilibrates with the environment. All right, so obviously coming soon, you got the exam tomorrow, review your chapters, you got the worksheets there, you got the YouTube videos, not only of Dr. Kim Smith about this topic, but the ones we record here, okay? And keep track of your sig figs. We learned the sig figs, we're gonna use them throughout the semester, okay? So sig figs are just because we're done with them for right now, we will use any calculation used throughout the semester would incorporate sig figs with respect to the final answer being presented with the correct sig figs, okay? All right, well, congratulations. We are done with this particular chapter. Any questions? Any questions you may have?
Yeah, can I ask a question about the lab due tonight?
Yes, go ahead.
one of the questions asked for examples of a state change.
Okay.
I was confused on what exactly you were looking for. Did you just want us to say, oh, it goes from the solid form of this to the liquid form of this at this temperature, or do we not have to list the temperature, or?
Oh, no, you can do like you just go up there in Google and say, let me see, show physical changes, and they'll give you examples. And that was a way to go look for other things other than ice going to liquid, going to gas, but other things out there that change a state. And they would ask you just to go find one that's interesting, and then just copy the link and present that.
Okay, thank you.
Okay, yeah, no problem. Nothing complicated. You just go find things out there that may be of interest to you.
And then we're not meeting next week, right? Because that's on the calendar, the next two, it says.
That is correct. That's a good point, Tyler. Next 2 Fridays, we're not meeting. So I will assign the videos for this chapter, and the next one, 5 and 6. And maybe a little 7. So those videos, 5, 6, and 7, you may want, you just take the time that you normally have here and view them, the ones from Dr. Kim.
Right. Thank you, Dr. Fred.
Yeah, no problem. Thank you. I forgot to make that point. So yeah, that's correct. You're welcome to come, but I won't be here. Okay. Now, if you have your,
That'd be funny. That'd be fun.
okay, you know,
Just kidding.
you guys, you know, you have your own, I mean, you have Zoom, some of you probably can, you know, it's free app. You guys feel free to, like the Discord, if you're not, you know, you don't want to do the Discord, you know, you Zoom or FaceTime each other, or, you know, set up some study time with each other. Okay. Feel free, because you can communicate with each other in Canvas. You can put it out there and say, all right, everybody, you know, I want to set up some time as a Zoom, who's interested, and go from there. Okay. And we're early in the semester, so this is a good time to get into the habit of doing that, because, you know, you'll find you can do that for all your classes and just stay on top. Don't risk getting behind, because it's a lot of work in playing catch up. All right. Any other questions, comments?
Yeah, I have a question. You said there's an exam due tomorrow?
Yeah.
Yeah, okay.
Exam chapters 1 through 3. It will open at 7 and close, I believe, at 11 p.m. So
Through,
you have
through Canvas or?
through Canvas, yes. And remember, you need to use your lockdown browser. So that was the whole idea of the lockdown browser, to download it, make sure you're ready to roll. And I think I only have 1 or 2 that haven't done it, but you can't access, if you go to Canvas like you normally do, and you click on the exam, it won't let you run it until you open up the lockdown browser. Okay?
Okay, sweet. Thank you.
No, you don't need no webcam. I wrote that in there, no webcam in there. I'm not gonna do the webcam. No, it's just the lockdown browser. Okay. Yeah, no webcam, you guys, because the lockdown browser keeps track. It won't. You have to close up a lot of applications. So that means, like, for example, the power, not the PowerPoint, but the if you need to, if you haven't done so, the tables, the periodic table and the shapes table, those are 2 of the tables that you should have a physical copy of, so you can access them if you need to get any information from them. Okay. And that means that with the lockdown browser, you won't be able to look at the digital. It will mark it as you're moving away someplace to do something else, which you don't want to do. Okay. All right. Yeah, I mean, I can't, I'm not going to use the webcam. The questions at open note, you know, I'm not there. I'm not there to watch you take this exam. Okay. And the only thing is just use the log, you need the lockdown browser and just stay with the exam. Because if it pops up and it logs that you went away, that infers that you're looking things up on the internet. Okay, and we don't want that. Now, if something happens, and it does happen, you're taking an exam and Canvas, or maybe you got Cox or something, or whatever internet service kind of causes a little bit of problem, do send me an email as soon as you can. I'll keep track tomorrow. I'll have your emails or come to me on the phone so I know what's up. If you got a question, I can answer right away. Let me know right away, and so I have record of that. Okay. Sometimes a glitch, it happens to me here lots of times. I'm here talking, and all of a sudden my signal just dissipates. Okay. Any questions? Any other thing? Because what I'm going to do is if you don't, I'm going to go ahead and jump into chapter 4. All right. So now we're going to get back to some chemistry, okay, and how things are put together. Okay. We're going to talk about the atoms and the model that we currently have about how the atoms are put together. And it's the fascinating aspect about this model that we have, we're always changing it. For example, we're adding to it, taking things away. The model we talk about today, next week, something else happens, and boom, we got a whole new model involved here. So it's a flowing model, but it is based on the experimental data that we have. It is the best model that we have. Okay, and I'll tell you this. We're going to deal with the 3 subatomic particles. Subatomic, they're particles that make up the atoms. The 3 that we're going to work with is what we call the proton, the neutron, and the electron. We're going to talk a little bit more about these in detail. The proton has been shown to have a positive charge. The neutron has been shown to have a neutral charge, no charge. And the electron has been shown to have a negative charge. It's a negative charge particle. Now, these particles in themselves are made up of even smaller particles, subatomic particles. Okay, that's beyond the scope of Chem 130. That's some high level stuff, and there's a lot of stuff going on right now, science-wise, to find the particle that makes up everything, all the protons, all the way up. And it's analogous to if I were to give you, like 1,000 little items. I'm having a senior moment, the little plastic things to make designs. I can make them all the same shape, the little plastic, all the same shape and same color. And if I gave them to you, 1,000 of them, I guarantee we're going to, and everybody works on it by themselves, we're going to come up with an infinite number of different designs. Legos, thank you. I was having a senior moment there. We're going to have all kinds of designs, and all of these designs are made up by these single particles. That's the thing that's really amazing. Then the other aspect is these crazy electrons. These crazy electrons are so tiny relative to the proton and the neutron, and yet they have a great effect on the chemical properties of all the chemistry involved here. And these are the properties that are running through your electronic device right now. The electrons are running through your electronic device to make your electronic device. This is the same things that are, excuse me, that give you that bad hair day, where they give you that frizz, or you're wearing pants or dress and they cling to you. These are electrostatic charges, and these crazy electrons have big time effect. Okay, so the models really begin, and this is the other amazing part, because some of the models begin in like in 1900s. Actually, it started in the 1800s, the models come in, but then around the 1900s, a lot of other scientists. This is the time period that Einstein was involved. Even though Einstein was involved with this particular models, there's a number of other scientists involved during this time period. It's just a whole slew of things were happening in physics and chemistry during this time period. Okay, so Dalton was he's the guy kind of started the whole thing. 1808, way back there. Okay, he proposed that an element is made up of tiny indestructible particles called atoms. Well, it turns out they're not indestructible. Okay, because these tiny atoms are made up, as I explained, of more particles in themselves, subatomic particles. Okay, so they were not indestructible. He also proposed that all atoms of an element are identical and have the same properties. Well, the first part of it is true. You know, I have, for example, carbon. Carbon is carbon, okay? However, carbon in the diamond has a totally different property than carbon in, say, graphite. Obviously, diamond is the hardest material on Earth, and it's made up of carbon. Whereas graphite is a dry lubricant, very slippery, and very hard. They're both made up, have carbon in them. Okay, same carbon, 6 protons, okay? But because they're the way they're put together and how they interact with each other, totally different properties. Okay. He proposed that atoms of different elements combine to form compounds, and that's our definition of a compound. So in this example, we have element green. Notice there's 2 of them together, so that suggests they're diatomic. And then we have element red. They combine to form a compound that consists of a red and a green bonded together. And actually, they make 2 of them. Now, this very dramatically demonstrates what we talk about the conservation of matter. That if I start off with 2 green atoms on the left, whatever they may be, when I'm done at the end of the day, I'm going to have 2 green atoms as a product. Here I got 2 green, and now I got number 1 and number 2 green as a product. They're in different forms, but it's still green. Okay, whatever that element is. The same is true with the red element. I got 2 of them here. They happen to be bonded together and being diatomic. And when I'm done with them, again, I will have 2 red elements. They're obviously not put together like they were as a reactant, but they are involved with respect to the compound that it created. And this is a conservation of matter, meaning that it's understood that we got a 1 here in front, that's a coefficient, and we got a 1 in front of the green. Change this color a little bit. Okay. Here it is up. And so it's understood there's a 1 molecule of my red and 1 molecule of my green. But then when I put everything together, I could really show this like this, put a 2 in front of the red-green compound. Just erase that, okay? And I have a bonded, I have a balanced, this is called balanced equation here, whatever this may be. 1 molecule of green plus 1 molecule of red, whatever it is, will give me 2 molecules of this red-green compound, okay? These coefficients represent these coefficients, and like I said, when there's no coefficient in front of it, it's understood to be a 1, gives me a ratio. Oh, we're back to ratios, huh? So I'm just gonna call this G for green and R for red. And so what I have here is a ratio of 1 G over 1 red. That's R. Or I have a ratio of 1 red over 1 green. Okay, Or I can have a ratio of 1 to 2 here, where I put 1 red numerator and 2 compound, whatever that may be, in the denominator. This ratio, like we just did with the calculations, will be utilized to help us calculate anything. We could say, all right, if I need 100 grams of this compound, how many greens do I need in grams to begin with? And I would use that particular ratio, balanced chemical equation. We're going to get into learning how to balance these chemical equations, because that number, that coefficient is extremely important in these calculations, okay? All right, so atoms of different elements combine to form compounds, okay? Another aspect about Dalton's atomic theory is that compounds in atoms are in whole numbers. So for example, H2O, everybody knows it as H2O. We put a subscript, okay, H2, which tells us there are 2 hydrogen atoms in a molecule of hot water. Now, 99% of the time when we write formulas, we would, the first element written is what we call the central atom. Normally there's a central atom, and then anything that's bonded to the central atom comes after that, okay? You'll always be told who the central atom. In this case here, by convention, H2O is written as H2O. Oxygen is a central atom. And we're going to learn how to draw formulas and structures, and water has this structure. This line that I put there represents a bond between the oxygen and the hydrogen. Notice there's 2 bonds there, okay? And so instead of writing it like I just did it structure-wise, we write it as H2O, and by convention, we put hydrogen first. But other things, for example, this is a formula for methane. We'll learn that in a bit. Carbon is written first. Carbon is a central atom. These 4 hydrogens that follow that are bonded around the central atom. Eventually, we will come up with a formula. We're going to learn how to do this that looks like something like this, where there are 4 lines around the carbon, and these lines connect the carbon with 1 hydrogen, okay? All right, the point is that all of these compounds, when they come together, regardless of what atoms are coming together, come together as whole numbers, not as half or 3/4 or anything in between. Whole numbers, all compounds consist, all atoms of a compound come together as whole numbers, okay? Another aspect is this, that atoms of 2 or more elements can form different compounds. And here's an example of 2 compounds that have in it carbon and oxygen. But the difference is the number of oxygens that are formed. We have here CO, which is carbon monoxide. And these 2 spheres represent carbon and oxygen, okay? Carbon is the gray color one. Then we also can have 2 oxygens bonded to the central carbon, and we will end up with carbon dioxide. So obviously you may have heard, I'm sure you've heard of carbon monoxide, very poisonous gas, one of the gases that our engines exhaust, and carbon dioxide, okay? Totally different. Plant life require carbon dioxide, okay? One of the byproducts that we create is carbon dioxide. So in our breathing, we get carbon dioxide coming out, okay? So that's why it's good to talk to your plants. Yeah, why is that? Because as you speak to them, yeah, you're giving them carbon dioxide. And what do the plants give you back? Anybody know? Oxygen, okay? So we have a very important relationship with plants. green light. All right, so and we got to be careful whether we write lowercase or uppercase, because given, let's say, carbon monoxide and lowercase, so we write that, this is cobalt, okay? And so we got to be very careful, you know, science is very exact. And so we have to be very exact here when we start writing formulas and how we're presenting your formula, okay? Because there's carbon monoxide versus CO cobalt, totally different species. All right. Now, we kick up to about 1897. This is the beginning where we get a lot of science is going on about the models of the atoms. And it's a pretty fascinating period. Now, JJ, I call him JJ Thomson. He is given credit for the discovery of the electron. Remember, those are one of the subatomic particles, the electron, back in 1897. What he did was he created what's called the cathode ray tube, which emits particles, okay? And these particles were focused onto the screen. On the screen contains a material that the electrons, it's about energy here again, listen, okay? So these particles have high energy and they're focused onto the screen. They hit the screen, they transfer that energy to the molecules of the screen. They absorb the energy and they get excited, what we call get excited from the ground state where we're at just minding our own business, and we get kicked up to the excited state. But nature being nature, we can't hang out in the excited state very long. We drop back down. And when we drop back down to the ground state, conservation of energy tells us that if I take up, absorb 10 units of energy, guess what? I'm going to release 10 units of energy, either in the form of light or in the form of heat, or both. And so that surface on that screen, those molecules, they emit that energy, light. And so that tells JJ, hey, something happened, okay? Something happened. Now, I was talking about this energy part for a second, okay? So this particle is doing this, all right? The screen will come here in the next example. I'm just kind of give you a little update. But here's the other aspect about this. Any charged particle that travels from point A to point B has with it a magnetic component, okay? Every extension cable that you use to pass electricity from point A to point B has with it an electronic component, perpendicular, magnetic component, okay? And so it's a good thing. Why? Because we can, with that aspect, that property, we can create electric motors, and we also create generators of electricity. So we play with the magnetic component, or we play with the charged species, which happens to be electrons. All right, we'll get to the particle here in a second. The fluorescence. Okay. But this is the beginning of what we now know as the old-fashioned television. If you have any at home, check your grandparents' home. They may have one where they got this old TV, no flat screen here, but even the flat screen uses similar principles as far as imaging what you see. The image you see on your screen and on the computer, those are particles on the surface of the screen that are being excited and then drop back down to give you light. This is happening so fast that you obviously can't see it. But this, JJ really unknowingly discovered the television, the precursor, the old school television with the big heavy rear end that had a magnets at the end of the at the other end of the screen. All right, so let's listen. Okay, and so here's the particle in red is being focused onto the screen, and then on the surface, that particle then transfers this energy to the molecule on the surface and results in a green fluorescence that the people looking at the screen here can see something happen, right? So this is what I mean by the beginning of the old school television, because this is the old screen on the far right here that you'll be viewing your cartoons or whatnot. Okay, so let's continue. Okay, so here, JJ takes a electrical field. Notice the negative on top, positive in the bottom, and look at what happens to that beam. It gets deflected. Specifically, it gets deflected to the direction of the plus charge. So that infers, does it not, that that red beam must be a negative charge, okay? And so a moving charged body has with it a component, a magnetic component. So what he does, he brings in the magnet, okay? And so with the magnet, there's a south side, it deflects that beam, okay? And if, FYI, a side note, the old fashioned televisions, that's why they were so heavy, was the fact in the back it had four big magnets. And these magnets, by adjusting the magnets, actually cause that beam to do a raster, go back and forth, back and forth, back and forth. Okay. Anyway, let us continue. Now, obviously, we're not going to get in detail at all with this equation. Basically, what the takeaway here is that JJ, was able to come up with this ratio of E over M. And knowing that information, it was now just a matter of finding some constants that he was able to calculate the mass of the electron. The mass of the electron. Obviously indirectly, the electrons are very tiny. It's not like we can put them on the balance and figure out how much they weigh. So you have to figure out how I can calculate that by alternative means. So that is the constant there, that ratio that he was able to calculate. All right. So based on this information and based on this data, this research in 1904, J.J. Thomson proposed a model of the atom, and it was kind of known as the plum pudding model. Okay, J.J. Thomson was a British scientist, so I'm assuming it has to do something with England, right? Plum pudding. So anyway, his model was kind of depicted here on the diagram on the right, where they think that these electrons were someplace in this pudding design here, right? Someplace, and that's where you show the electrons all over the place. And then having a plus charge, there must be a negative component to the atom. All right. So That was the model, the plum pudding. And that lasted for a little bit until Rutherford, okay? So notice JJ's 1904. Now here comes another scientist, English scientist, Ernest Rutherford. And he worked with what were called alpha particles. Now, the thing about alpha particles, they are much, much bigger than the particles seen here, okay? And so what the experiment he did was generate these large, heavy particles, and he focused them onto a foil of gold. Gold is a very big, hefty atom, okay? And it was surrounded by this similar type of detector that JJ had. And so these particles would hit the surface of the detector, the screen, and then emanate a light. What he found was very fascinating in that based on the plum pudding model, these particles should just generally just shoot right through there because they're big particles, all right? But what was happening, some of the particles were being deflected. And that suggested that there must be something very heavy in the atom, much heavier than the electron. They wouldn't deflect. Electrons are very tiny. That was determined by JJ, okay? And so there must be something that's very heavy causing these particles to be deflected, right? And some of them were deflected right back to the sensor. You know, it's similar to what they want to suggest is, you know, firing a bullet through a Kleenex and it bounces right back to you to give you a perspective here. Okay, so here's Rutherford. Sorry. So you can see here that the majority of particles were hitting here on the opposite side of the gold, and the screen was being lit up. But then there were some particles that were being deflected, okay? And so the screen was being lit up in different angles. And it's like, you know, shooting pool. You know, you can hit the corner pocket. I got to hit the cue ball, hit that ball just right to get it, shoot at an angle. And so that really surprised Rutherford and actually proposed a totally different model. So let's continue here. Okay. And so Thompson's model to the left was basically the plum pudding model. And then based on Rutherford's datum, suggesting that there's got to be something in the atom that's pretty hefty to cause those particles to be deflected, he proposed that there must be a nucleus, okay? A component that's a lot bigger than those particles. So he is credited with discovering what we now know as the proton / nucleus, because we find out later, not until the 30s, Chadwick actually is discovered the neutron, okay? And so we have in the model, very analogous to the diagram that we have here on the right, where in the center is where the proton is and where the neutrons is. And then the electrons are somewhere orbiting, you know, sort of like our solar system around the nucleus. We will learn because of the mass of the electrons, that the electrons actually exist in different energy levels, okay? And because the mass of electrons is so tiny, it acts like light. It behaves as light does. And we're going to learn that there are 7 energy levels. Now, if you look at that periodic table, you will find the horizontal rows. There are 7 of them. They represent 7 energy levels that we have, okay? Just FYI. I'll make mention of that later on. Also, based on all this is that the atom is basically empty space, you know, with electrons around the nucleus. And there's a very large, strong force between the positive nucleus and the neutron and the electron. There's a very strong force. Nuclear fission, okay, atomic bombs. This is the breaking up of atoms, and we all seen pictures of atomic bombs and how devastating they can be with respect to the force. So there's a lot of energy in these atoms. If I were to be, for example, a hydrogen atom, and let's say I was scaled to be the size of a hydrogen atom. Hydrogen is the first element. I have 1 proton and it has 1 electron. My electron will be roughly about 3/4 of a mile away, ballpark, if I scaled everything up. To give you an idea of the distance and the empty space in between, but yet there's a lot of strong force in the traction that's holding this hydrogen atom together, okay? So each atom has a small dense nucleus where the protons and neutrons exist. Another analogy would be if a nucleus is the size of a small marble, then the atom is approximately the size of a Cardinals stadium. So a lot of space in between. All right, so we have the subatomic particles that we're going to work with. The electron, the proton, and the neutron, okay? They each have a symbol given here. Lowercase c with a super negative symbol that represents the electron. All right, the proton is the lowercase p with a positive because it has a positive charge, and the lowercase n for the neutron. This location or position, electrons are outside the nucleus, and the proton and the neutrons are obviously in the nucleus. And then the column with the charge gives the respective charge. Now, the proton defines the element. There are 118 elements, okay? Element number 1 is hydrogen. Element number 2 is helium. The difference between element 1 and 2 is 1 proton. Helium has 2 protons. Hydrogen has a 1 proton, okay? And it continues, lithium. So as I go across the periodic table to a higher number, that tells me the number of protons that element has, and that defines what that element is. Electrons, we're going to learn, we can lose and gain electrons all day long, but we don't change what that element is, okay? Point number 1, put it in long-term memory. All metals lose electrons, okay? Keep this in mind. If an electron is a negative charge, and if I lose a negative charge, can anybody tell me what kind of new charge I would have? Maybe, okay, what we got here? A positive, that is correct, okay? And if you don't see it, look at it this way. Think of it in psychological terms. Obviously, a negative person, negative attitude, if they lose negativity, they become more positive, right? Okay. The same is true if you gain negativity, and from a psychological standpoint, you become more negative. And so all metals, by losing electrons, end up having a net positive charge. And we call those ions. More on those later on. That is what you are ingesting. When you are drinking electrolytes and so forth after a workout, you are drinking metals and so forth, or if you're ingesting vitamins, or what you are doing are ingesting not the elements, okay, but you may for a couple, but for the majority of them are the ions, and the ions are nothing more than the elements that either have gained or lost electrons. When you put sodium chloride on your French fries, table salt, you are not putting sodium metal, or nor you are putting chlorine gas on your French fries. You are putting sodium chloride. The metal is sodium, it loses an electron, has a positive charge. The chloride, being a non-metal, put that in long-term memory, gains electrons, okay? And it has a negative charge. So gaining electrons, you have a negative charge, and all non-metals gain electrons, okay? The driving force that we're going to learn is by losing and gaining electrons, we want to get to the, quote, magical 8 value, the octet. Literally every ionic compounds are out there, totally out there, okay? Yes, there are non-ionic compounds out there, but there a lot of them metals, just by nature of the beast, when they get to the environment, they break down. And when they break down, they generally go into ionic form. Okay. Your body is loaded with ions. Your body couldn't function without the ions. And these ions could be neurotransmitters that have a charge, okay? Or they could be sodium, potassium. Sodium is if you have high blood pressure, it's not good for you, but sodium is very important in muscle contraction. Potassium is potassium ion. These are ions. Potassium is extremely important in multiple things. One of them is blood clotting, involved blood clotting. So the metals themselves wouldn't function as the ions. Just breathing here, hemoglobin is in the center, and iron. That's why you got to ingest iron, but it's a ionic iron. And because of that property, it hooks up with hemoglobin, and it will pick up or hold 4 molecules of oxygen or 4 molecules of carbon dioxide, or any combination thereof, and it's reversible. But once you inhale carbon monoxide, it's no longer, you messed up your hemoglobin, your ability to transfer oxygen. Anyway, side note, sorry, I get a little bit sidetracked, because it amazes me that these ions, these elements, when they losing 1 or 2 electrons, remember they're tiny, and by losing those few electrons, man, they have a great effect, a big effect on everything. And something to think about here. Anytime you grasp something, now think about this, our model. We got the nucleus in the center, and the electrons on the outside orbiting, right? Well, electrons have negative charge. So when you grasp something, and I'm grasping this pen, or even another finger, on the surface of those are atoms, okay? And those are electrons, and they repel each other. All right, so I'm never really grabbing anything, because I'm holding on to something that never touches, because I can't bring 2 electrons any closer, or any electrons cloud any closer, because they're going to repel each other. All right, so anyway, food for thought there. The relative mass, what that is simply put, they're tiny, very small mass for all the subatomic particles. So instead of working with these, extremely tiny numbers, they give them a relative mass, a AMU, atomic mass unit. Okay, they assign the proton and the neutron, because their masses are relatively about the same. They gave them a AMU of a 1 value. It's analogous to me. Let's say I'm 200 pounds, yeah, on a good day, 200 pounds, and somebody else is 400 pounds. So I am a relative weight 1, and that person at 400 pounds is twice my weight, right? So they have an AMU of 2. That's what they're talking about. It's a relative weight. So I assign 1 and 1 for the proton and neutron. The electron, on the other hand, is basically given an approximate 0 because that weight is so tiny and so small that it is treated as a 0 weight. Obviously, it does have mass to it. You know, JJ's shown that it does in his calculations and his experiments, but their weight's so small, it's basically 0. And because of that, it behaves, has a lot of behavior like light. And we'll learn more about that. And we're going to learn that these electrons are actually in specific energy levels. All right, so that's about it. Atomic notation. So we have all these elements. So let me call up the periodic table real quick because I do refer to it quite a bit. Okay. Right, so if you look at your periodic table, you'll notice that we have 118. Now this one hasn't been updated yet. We're gonna have to get it updated, but elements, oh yeah, it has been updated. Yeah, it's good. 115, 117, oh, too many. 118, these were discovered about 2015, I think. And so that basically at one time we had just letters, temporary letters there. And then the world got together. There's a scientific organization that gets together and decides what they're going to name them. So they got a name now. There's 118 elements, okay? Now, every element has a symbol, be it a 1-letter symbol or a 2-letter symbol. Second letter is lowercase. So we have hydrogen, number 1, okay? For example, then we've got Li, which is lithium, all right? So we did talk about, if you didn't be familiar with at least the first 20, and we're gonna have more of them as we progress. Be familiar with respect to name and their symbol. Now, if you look at the periodic table, you have the symbol. Above that, you have the atomic number. It is a whole number, okay? So lithium is element number 3, okay? What that whole number tells me this, 2 things, 2 bits of information it tells me. 1, it tells me how many protons that element has and how many electrons. So lithium has 3 protons and 3 electrons, okay? If we look at K, which is Kalium, which is actually potassium, it has 19 protons and 19 electrons. If you have 19 positives and 19 negatives, what is your net charge? You can tell me that. If I have 19 positives numbers and 19 negative numbers, what net do I have? 0, exactly, okay? So all the elements up here on the periodic table, all elements have a net charge of 0, okay? Net charge of 0. When you start losing and gaining electrons, that net changes, and therefore you end up either with a net positive, could be a positive 1, could be a positive 2, could be a positive 3. It all depends, okay? Or it can pick up electrons, which could be a negative 3, negative 2, negative 1, okay? Now I'm going to tell you something here, and then we're going to come back to it. But you see that Roman numeral up front? Up there, I just highlighted the Roman numeral 1, okay? A. This is only true for the A element. So when I have Roman numeral 1, you see, as you go across the periodic table, you have a column number, Roman numeral 1, Roman numeral 2, okay? What that tells you is this, that every element in that same column, let me highlight that, okay? Every element in the same column here, all of them, regardless of what it is, though they have different number of total electrons, what they have in common is that they all have one electron in the outermost shell of the energy. Because earlier I said there are 7 energy levels, okay? I'm jumping a little bit ahead of myself, but I think it's a good time to introduce this. For example, I'm gonna bring another periodic table, but I'm gonna do it by hand. I will take my periodic table and I'll do this. 1, 2, 3, 4, 5, 6, and 7. Okay. 7 energy levels. Everybody in that first column 1A has 1 electron in the outermost shell. For example, sodium is number 11. It has 11 electrons. Okay. Of those 11 electrons, one of them will be in the outermost shell. Sodium being in the third energy level, the 10 would be fill in the 1 and the 2 energy level, and then energy level number 3 will have 1 electron. Potassium has 19 electrons. Obviously got 8 more than sodium, but it shares the fact that one of them in energy level number 4, 1 electron exists there. The other 18 are in energy level 1, 2, and 3. And because of that 1 energy level, 1 electron in the outermost shell, everybody in that group shares the similar type of reactivity. Because all the action, when it comes to chemical reactions, happens on the outermost shell. You know, if you think about it, you know, we're going to cut into a watermelon. Obviously, we're not cutting from the inside out. That's ridiculous, right? We're cutting on the outside. That's where the action begins, on the outside. So all chemistry begins with the outermost shell, okay? So these guys over here all have 1 valence electron, and that's why they act very similar. Lithium and sodium and potassium and so forth all have similar reactivity simply because they share the property of having 1 valence electron. So with that information, take that, everything I just told you about group 1A, and transfer it over to group 2A. Okay, this is beryllium. What would you say that everybody in group 2A have in common with respect to electrons?
They have 2 electrons in their valence shell.
You got it, exactly. Everybody has 2 valence electrons, what we call the valence shell, the outermost shell. And so magnesium is in right here. Okay, it has 12 electrons. Of those 12 electrons, it has 2 of them in the outermost shell, which happens to be an energy level number 3, just like sodium. Calcium, right here, has 20 electrons. Okay, 20 protons, 20 electrons, and 2 of them in the outermost shell. It happens to be energy level number 4. Okay, and these guys in this group all had the same reactivity simply because they had shared the same number of valence electrons, and therefore they will react very similar. Okay, now we can't do that with the guys that are labeled B. Wish we could, but you know, we can't do the predictions we just did for groups 1 and 2. All right, so the guys in B, the B elements that are labeled in there, they vary. All right, they vary with respect to how many electrons they have and how many they lose and so forth. Let me, before I leave this part, I got one more thing to tell you. With the exception of hydrogen, all the metals in here in group 1 will lose 1 electron. Okay, and that being the case, sodium by losing one electron, now has a positive charge. And that is what you're putting on your French fries, not the sodium metal, but the sodium ion. And it has a +1 charge because that one valence electron is out there all by itself. And Mother Nature doesn't like to deal with, unstable energy levels because it takes energy to maintain that one electron in energy level number 3. And you think about it, it's easier to get rid of that one than to deal with it. So sodium will very readily get rid of one, and it ends up with a +1 charge as an ion. Magnesium has 2. What would you predict the ionic form of magnesium would be? What charge would that be? Obviously, it's a plus. Why? Because it's a metal. All metals will lose electrons, it becomes plus. But what would be the magnitude of magnesium ion? What do you think? What would you, if sodium had a +1 and it had 1 valence electron, magnesium had 2 valence electrons, what would you think its ionic form charge would be? Plus what? +2. Those 2 electrons that magnesium has, 2 electrons, and the outermost shell, too much energy you have to take care of. Easier to get rid of it because it's a metal. I'm going to get rid of it. Now I have 10 electrons to deal with, and I'm happy. Sodium had 11, now has 10 as an ion. Okay, so the driving force, and we're going to learn more about that here, is 8, is the magical 8. But these are the guys that we are ingesting. Calcium, the same thing, will be a +2. When you need calcium for your bone development, you're dealing with ionic. At the other end of the spectrum are the nonmetals. And I don't want to take too much time on that, but they gain electrons. And specifically, depending on the group that they're in, they will gain electrons. Now, if we look at fluorine, what Roman numeral is fluorine? That's Roman numeral 7, okay? And it's a non-metal. Being a non-metal, fluorine wants to gain electrons. The question is, well, how many does it gain? And the answer is, it depends on the group that it's in. It's in group 7. It wants to get to that magical 8. How many more does it need to gain 1? To get that magical 8. It only needs 1 electron. So fluorine, which has 9 valence electrons, 9 electrons. Of those 9 electrons, 7 of them on the outermost shell, okay? So all he needs is 1 electron to fulfill that magical 8. Now it's happy. And then what happens is, because of that, it now has a fluorine, now has a -1 charge. That is what you're using when you brush your teeth. We changed its name to fluoride when it becomes ionic. And the driving force again, because everybody here has in common 7 valence electrons as an element. They're only 1 away to get that magical 8. And everybody there will gain 1 electron. And everybody there in that box will have a negative charge. And everybody gets their name changed by gaining electrons. So fluorine becomes fluoride. Chlorine becomes chloride and has a -1 charge. Okay. And that's what you put on your French fries, the chloride. Fluoride, read your toothpaste. You may have stannous fluoride, which is tin, T-I-N. Fluoride, which is a salt, ionic compound. Or some toothpastes have a sodium fluoride. Okay. All right. So let me gather back. So from the periodic table, you know how many protons, how many electrons. Okay. And we represent the elements with the following method. We use what's called the scientific notation. SY represents the symbol, whatever symbol the element is. Now, superscript left, okay, left, not right. You see where the A is? That is the mass number, okay? And Z, subscript left, Z represents the atomic number. All right, so we can get the symbol from the periodic table. We know what that is. Also, the periodic table tells us what the atomic number is. It's on top of the symbol. What we don't know at this point is what we call the mass number, okay? Well, the mass number, remember this, it's whole number. Always be a whole number. Atomic number, always a whole number. Atomic, whoa. Atomic, yep. Atomic weight or mass is a decimal number. Okay? Decimal number. Now, back to the product table. I told you I referred to it quite a bit. Let's take a look at carbon. Carbon's number 6. Carbon has 6 protons, 6 electrons. So earlier when we talked about carbon monoxide or carbon dioxide, 2 different forms, types of carbon, but the thing, what they have in common, the carbon in carbon monoxide and the carbon in carbon dioxide still has 6 protons, okay? Protons define what the element is. We can change and lose neutrons and electrons all day, but we can't change protons without losing the identity, which brings me to a point. I don't know if you know what an alchemist is. You ever heard of that? Here's lead, here's gold. Alchemists for centuries have been trying to make gold from lead. Okay, so here's a symbol for lead, 82, element 82, gold's number 79. How many protons does gold have?
79.
79. Lead has 82, okay? And so for lead to become gold would have to lose how many protons?
3.
3, you got it. Where the protons are again, they're in the nucleus, a lot of energy. And so for that to occur and not blow yourself up to kingdom come, kind of challenging, okay? Because, you know, you start messing with the nucleus and you got problems. And, you know, that's why you got atomic bombs, you know, they had undergo fission. Fission is they're breaking apart and you got to break the nucleus, which has a lot of energy. As compared to fusion, which is occurring on the sun, where molecules are coming together, hydrogen's coming together to make helium. Eventually the sun's gonna blink out because it's gonna use up all the hydrogen. Hopefully not today, but it'll take a while. But there's a lot of energy in fusion, but not have all the side problems that fission has. So it'd be kind of tough to make gold from lead and not having a series of problems, okay? So unless there's some chemistry involved there we're not familiar with, and if you come up with that, let us know and we'll patent it. But then if you do that, then you flood the market of gold and then its price goes down, so you haven't done anything, right? It just made matters worse. All right, so underneath each element symbol is a number, decimal number. That is the atomic mass. It is a decimal number, not a whole. And I will explain why it's a decimal number here in a second. Yeah, it is the average of whole numbers. And like we take a number like 4 and 5, we want to average those 2 numbers. We got, 9 divided by 2, we got 4.5, right? So that decimal number 4.5, that number 4.5 comes from whole numbers. And because it comes from whole numbers, and I'll explain why it comes from whole numbers, it is, these numbers are not used in determining your sig figs. The atomic weights are not. Because the averaging of whole numbers ends up with numbers that have an infinite number of sig figs. So we don't utilize it. So don't use the atomic weights. But what we can do to figure out the atomic number, the mass number, is to take the 12.01 and round it up to the nearest whole number. So for carbon, it is 12, right? 12.01 rounded up to the nearest whole number is 12. Nitrogen's right here. Make that 14 for nitrogen. Boron, which is number 5, that would be 11, okay? And you see we are just round that up. And what that does is that gives you the mass number for the most common, I'm throwing in a word here, common isotope of that element, okay? We're gonna learn the function, the purpose of the neutron is twofold. One, it helps stabilize the nucleus for one, as we add more protons into the positive charge. But second of all, as we add, the neutron defines the type of isotope an element has. An element will be an element. There are what are called isotopes that are still that particular element, but they have different properties because they have different number of neutrons. We're all familiar or heard about carbon-14 dating, okay? Well, carbon has 12 neutrons, and that is the most common isotope of carbon. And that's why I can take that 12.01 and round it up. But there is carbon-14. Thing is that carbon-14 is not as common as carbon-12. And so when we take the average of all these whole numbers, there's carbon-11, carbon-12, carbon-13, carbon-14, whole numbers, right? Each one has a separate amount, percentage brought to the table. Carbon-12 is 98, 99% in the nature. Okay, it doesn't take away from carbon-14 or the other isotopes. Okay, it just that carbon-12 is the most common. So when we average 11, 12, 13, and 14, we don't get a number in between. We get a number that is closest to the most common number that is, in this case, 12. So hence we get 12.01. Okay, and so we can figure out the mass number using the atomic weight of the most common isotope on the periodic table. Okay. And that gives us the mass number. So we would write that this was carbon, and questions ask you to write the atomic notation of carbon. We're going to have to assume that this is the most common isotope they are talking about. And we will write C for carbon, 12 and 6. So that will be the atomic notation for carbon 12. Okay. Or they may say, write the atomic notation, it'll write its name and then do carbon-12. While they're telling you carbon-12, they're telling you what mass number to use, okay? Because it could have been carbon-14, okay? Well, in that case, it is carbon, 14, and 6. It still has the same number, the same atomic number, okay? That doesn't change. It's still carbon. The only difference between carbon-12 and carbon-14 is that 14 has 2 extra neutrons. That's why it picked up, remember the AMU of a neutron is 1? So its mass number goes up by 2. And carbon-13 will be as follows, okay? And there's even a carbon-11. Okay, all of these are isotopes, 11, 12, 13, and 14, and they only differ from each other by the number of neutrons that it has. And literally every element up there has isotopes. Hydrogen, we got hydrogen 1, there's hydrogen 2 and hydrogen 3. Okay. Some only have a couple, some have quite a number of them, but let's do one more here. All right, so what this, let me regroup here for a second. Refresh your memory. Atomic number from the periodic table tells you the number of protons and the number of electrons. Number of positives, and number of negatives. Net zero. So all elements have a net zero charge. Okay. The ions are the ones that either losing or gaining. So if we take the mass number and want to know what the mass number is, it is the sum of the number of protons and the number of neutrons, okay, which are whole numbers. Okay, so the mass number, if we don't know the number of neutrons, what we do is we can rearrange this equation and just say that number of neutrons is equal to the mass number minus the number of protons. Isn't that true, right? This equation down here. Here's the mass number, which is the whole number. Here's the number of protons or number of neutrons. If we're looking for this, then you just move the protons over. Mass number minus protons, okay? Which is also the number of electrons, right? Because this is also true. And we can calculate the number of neutrons, which again, these are all whole numbers. Right. Every atom has the same number of protons, okay? As I stated, number of protons equal number of electrons. The number of protons defines what an element is, okay? Carbon always will have 6 protons. Hydrogen will always have 1, so on and so forth, okay? That's what makes that element carbon. Atomic mass units, we talked about that. These are relative mass units. The mass of the proton and the mass of the neutrons are approximately 1 AMU, one value, where the electrons have no mass, okay? Treated as 0. Mass number is equal to the number of protons plus the number of neutrons. We can rearrange that to calculate the number of neutrons by taking the mass number and subtracting the number of protons it has, okay? When we're not given the mass number, we can assume that the mass number is the most common isotope, so we can take that, go take the periodic table and just average out the atomic weight to the nearest whole number, and that gives us the mass number. And we subtract the number of protons, and we got the number of neutrons. Okay. Yeah. And that is for the most common isotope, because we're not always working with the most common isotope. So the periodic table shows the most common isotope atomic weight by by taking the whole number of the atomic weight, okay? For example, let's take a look at this. Here they're saying, write the atomic notation for potassium 40. Well, whoa, they're telling you that bit of information. They gave it to you, okay? They're telling you what the mass number is right there. Now you might ask yourself a question. Is potassium 40 the most common isotope in the periodic table? Well, to answer that, you go to the periodic table and you search for potassium. Okay, potassium is right here, number 19. If we take the 39.10, round it up to the nearest whole number, the most common isotope is potassium 39. The problem is talking about potassium 40. Okay. Now, what they both have in common is the number 19. Number 19, the atomic number. And so we found the symbol, which is K. Okay. Potassium 40 is given to you. You don't have to do anything unless they would have said, you know, potassium, just potassium. When they don't give you the hyphen 40, you can assume they're talking about the most common isotope. So you can go to the periodic table and then, you know, you're talking about 39, but they gave you the 40. So we're talking about potassium 40. So the atomic notation is 40 on the left, superscript left, and 19 subscript left. If this was the most common isotope, then potassium 39 will be written as follows. Okay. Now the question is, well, how many neutrons are they for potassium 40? Well, all we got to do is subtract this number here, 40 minus 19. Okay. And we get 21. So potassium 40 has 21 neutrons. How many neutrons does potassium 39 have?
$20.
Exactly. Exactly, because, and that's the only difference between the two, okay? Is that if this was the hydrogen, these are the three isotopes of hydrogen, okay? The only differ is that hydrogen, the most common isotope of hydrogen is hydrogen 1, has 0 neutrons. Hydrogen 2 has 1 neutron, hydrogen 3 has 2 neutrons. And this hydrogen 2 is utilized to make heavy water, D2O, okay? So that's what isotopes do. Isotopes define the neutrons define the isotopes that each element may have, okay? Here we go with write the atomic notation for bromine 81. Question here. Okay, no problem. You guys need to leave. Not a problem. You want to take a quick break? Why don't we do that? I got carried away here. We're almost done with this chapter, by the way. Why don't we take a quick break? And if you have any questions, we will cut it off there. And let's just take, say, a 10-minute break. I got 2:08. Let's come back at 2:20. How's that? Okay. All right. See you at 2:20. Okay, sorry, got tied up here. Well, let us continue and then we'll be done here with this. All right, so here the question asked is write the atomic notation for bromine 81. And out of curiosity, you might say, is that the most common one? Well, let's go find bromine on the periodic table. And bromine is element number 35. It has an atomic weight of 79.90. Which tells you that the most common isotope is bromine 80. Okay, so obviously in that question, they are not talking about the most common isotope for bromine. And so we found the symbol as BR, lowercase r, don't forget that, it's not uppercase. And 81 is given to you there. You didn't have to calculate anything. And then from the periodic table, you will determine the number of protons from the atomic number, excuse me. The atomic number gives you, it is 35. And so going back to what we did, the most common isotope, its symbol would be, notation I should say, would be bromine 80, okay? And the number of neutrons would simply be 81 minus 35, so that would be number of neutrons for bromine 81. this one. Okay, over here, this would be 80 neutrons. Excuse me, not 80, what am I saying? 45 neutrons for bromine 80. Okay. So that is the manner of writing the atomic notation. One, you need to get the symbol. Two, you need to get the atomic, the mass number, which either they will give it to you in this format, or they may just say just bromine. And if they just say bromine, then they're assuming the assumption you can make legitimately is that we're talking about the most common isotope. So you're talking about bromine 80, and then the 35 that you need to add. And make sure that it is on the format is these numbers are on the left side of the symbol, okay? Superscript left, subscript left. Okay. All right. Clear the mess here. All right, so in continuation and talking about isotopes, and like I stated earlier, there are isotopes of carbon, the most common being carbon 12, but there is also carbon 13 and carbon 14, okay? There's also carbon 11. They all have 14 protons, okay? Because they're carbon, all of them, regardless of the isotope number. Where they differ is in the number of neutrons. And if we had included in here carbon 11, okay, then this would be 5, okay? And if we needed to write the symbol, the notation, then we got carbon 11, carbon 12, carbon 13, and carbon 14, okay? All of them are carbon, all have same number of protons. The only differ is in the number of neutrons. And even that difference does have an effect on the physical properties of the compound, okay? For example, earlier, we were talking about density, and I said H2O. When that freezes, when H2O ice cubes, you know, we make ice cube from H2O, that they float because of the volume increases, so that ratio gets less than 1. If you use D2O, which is the deuterated water, that is the isotope of hydrogen, and you freeze it, it looks the same. It actually does not float. It drops like a rock because it has a higher density. Okay. All right. So let me clear. You may get a table as follows, and where they're listing the elements, different isotopes. In this case, we got oxygen 16, oxygen 17, oxygen 18, okay? Now, they want the mass number, so the first column is pretty self-explanatory because it's given to you, okay? You don't have to determine or calculate anything. Right there. That is the mass number. Remember, it's a whole number. Number of protons, well, you got to go to the periodic table, look up oxygen, find out the number of protons, which also tells you the number of electrons, okay? So these two are the same. Now, where they differ, obviously, is the number of neutrons, and it's simply 16 minus 8, 17 minus 8, 18 minus 8, and that is the number of neutrons. And so the most common isotope is carbon 16, and I know that by going to the periodic table. Look at the atomic weight, you see it to be 16.01. And so that tells me automatically the most common isotope is oxygen 16. Okay. Now, I explained briefly before why the atomic weight is a decimal number, because it is the average of these four whole numbers, okay? Carbon 11, carbon 12, carbon 13, carbon 14. And much like the grade that you get, the final grade, there is a weighted percentage of the assignment and the labs and so forth. And so there's a different amount of contribution that each component brings to the final number, and that's what's happening here. Carbon 12 is the most common isotope out there. It's made up of almost 98% or 99%, 98.89%. The next one is carbon 11, 13, excuse me, set at 1%. And so if I were to say average the numbers here, simply without taking into account the contribution that each one brings. So take the average by the whole numbers would be what, 12 and a half, right? 12 and a half. But because there's more carbon 12, it brings more contribution. The overall atomic weight, the average, turns out to be 12.01 because there's a lot more contribution from the carbon 12 than the rest of the isotopes. And that is why we can take that atomic weight in the periodic table and round it up to the nearest whole number, and that gives us the mass number for the most common isotope or the most abundant isotope for that particular element, okay? And because of this, because we're taking the average, the weighted average of the whole numbers, again, the atomic weight has really an infinite number of sig figs. And so we don't utilize the atomic weights in any calculation that we need to determine sig figs, okay? All right, let's clear that up and what's abundant. All right, so you might be given the periodic table and you're asked the question, all right, which is the most abundant isotope? And so obviously you're gonna need the periodic table, and we're gonna share that again. And then obviously we're gonna go find out the symbol for lithium. Lithium is Li, which is number 3 right here. You'll find the atomic weight of lithium is 6.94. Rounded up to the nearest whole number. That tells you that lithium 7 is the most abundant isotope of lithium, okay? Chlorine 35 or chlorine 37, we do the same thing, periodic table, okay? Go find chlorine, which is number 17, right here. And that has the atomic weight of 35.45. Round that up, becomes 35. So chlorine 35 is the most abundant isotope. So we can circle that one, okay? The only difference between that 35, chlorine 35 and 37 is 2 isotopes. For lithium 6 and lithium 7, excuse me, what I just say. The difference between chlorine 35 and 37 is 2 neutrons. And 1 neutron for lithium 6 and lithium 7, okay? All right, a lot of elements are radioactive and very unstable, okay? They start to break apart, and when they do break apart, they release energy, and a lot of them release some very strong energy, okay? Radiation, just as these particles, alpha particles, beta particles, gamma particles. We just need to know that they release energy, okay? We have what we'll find that on the periodic table, the ones with parentheses, like curium 247, that's just telling you that it's pretty unstable and therefore can't really get a good accurate measurement with respect to finding all the isotopes and the percent concentration and coming up with the atomic weight. So that being the case, they anything that is in parentheses with respect to atomic weights are radioactive and break apart. Curium, Cm, that's an interesting element. It's named after Madame Curie. I find her to be a very extremely fascinating woman. Just curious, a little side note, anybody know where Madame Curie was originally from? A lot of people mistakenly say France, but that's not correct. Yeah, okay. Madame Curie was originally from Poland. She is one of the few scientists that have won 2 Nobel Prizes. 2 Nobel Prizes. Her background, like I said, she is a chemist by background. She extracted, processed like a ton of earth to find her element that she discovered, radium. Yeah, radium. And she was very instrumental in the use of X-rays, using X-ray machines and so forth. She actually died from a blood disorder due to exposure to radioactive material. We didn't know much how radioactive material behaved, and she did suffer the consequences. She originally came from Poland, and the reason she came to France was, at the time, France was the mecca of all science, and Poland did not allow women to get a higher education. Excuse me, yeah, Poland. So that's why she went to France. And so, anyway, her kids also won the Nobel Prize, so very smart lady. All right, so this brings us to what we call chemical formulas. Now, we're going to do a lot of this down the road. Right now, what we're trying just to present here is to identify how many atoms, given a chemical formula, and that is a description of how many atoms of each element are in a compound. We need to be able to identify how many of each are there, okay? Doesn't tell us anything about how things are bonded. We're going to learn more about that with time, okay? If a symbol has no subscript, it's understood to be a 1, just like in mathematics, leave it blank. So for example, we have H2O that says there's 2 hydrogen atoms and the oxygen, 1 oxygen, okay? So it's a total of 3 atoms for a molecule of H2O. It doesn't say that hydrogen is bonded to hydrogen. We're going to learn eventually with time here, because you'll be told who the central atom is. There's always a central atom, and then whatever's attached next, following that element-wise, symbol-wise, is bonded or attached to the central atom. So the structure of H2O is not that. Something interesting, you might want to Google dihydrogen monoxide, okay? Dihydrogen monoxide. You'll be surprised what comes up. The hazards of dihydrogen monoxide, which is water, okay? Yeah, they could be hazardous for you if you can't swim and things like that, but it's just an example of taking information and making it sound pretty bad. Anyway, let's take a look at this formula. We got a chemical formula here of C3H3O3. Not concerned about the structure at this time and what it is, okay? We will learn that eventually. That is, some of you may eat that. The C3H6O3 is actually a very general formula the way it's written. It is actually can represent a multiple of compounds, and this one could be acetic acid, aka vinegar. All right. Anyway, takeaway from here is that there are 3 carbons. Okay. There are 6 hydrogens, and there are 3 oxygen atoms in this molecule for a total of 12 atoms. Okay, so we need to recognize how many of each. Why? Because down the road, we're gonna need to determine how many atoms of each. So in this case, there's 3 atoms, of carbon. Each one has an atomic weight of 12.01. So we would take 3 times 12.01, so multiply that, get that number. There's 6 hydrogens. Each hydrogen has an atomic weight of 1.01. So it's 6 times 1.01. We add that to the number of total carbons. And then there are 3 oxygens at 16 each. So 3 times 16, we add that up to the final tally. Add all that up, and that gives us what we call the molar mass for that structure. Okay, the molar mass. And we're going to be able to calculate a multiple things for our calculations, but more importantly, we can also calculate the percent composition of carbon, the percent composition of hydrogen, and the percent composition of oxygen. Okay, we'll give an example of that in a second. All right, here's another one. Now, the takeaway from here is this. Notice in this structure, we got a parentheses. Okay, that's a flag for you to be aware of something. I'm going to direct you to the periodic table because we're going to be using this table quite a bit. Not just this part of the table, but right below the periodic table, there is another table called the most common polyatomic ions. Notice that they all have a charge, superscript charge, but these are called polyatomic ions. Normally, ions are made up of single elements or whatever they be, like sodium by itself, chloride by itself. So there are ions that are bonded together and have an overall charge, and this is one of them. Okay, so this is polyatomic ions, and be familiar with these because we're going to be able to combine these and make a variety of compounds. All right, so let's go back to this one. Oh, before I leave it, notice the one here I just mentioned, the parentheses. In parentheses, the polyatomic ion has a name called ammonia. The name here for these polyatomic ions, that's what they are. We don't change them. That NH4 -1 has a name called the ammonium ion. The C2H3O2 negative is called the acetate, so on and so forth. Note the majority of ions that we utilize or have a negative charge compared to one positive up here that we use ammonium. Okay, so there are 2 ammonium polyatomic ions in this compound. All right, 2. And we got CO3 that we're going to learn to recognize it's also a polyatomic ion called carbonate, CO3. But right now we just want to know how many atoms of each. So we have 2 nitrogens, you can hopefully see that, and there are 8 hydrogens for the total number of the 2 ammonium polyatomic ions. That means we got a total of 14 atoms. There are 2 nitrogens, 8 hydrogens, 1 carbon, and 3 oxygens. Okay. That, by the way, this structure example is called ammonium carbonate. Ammonium carbonate. All right, here's a few more. This one is H3PO4, also known as phosphoric acid. If you drink a lot of soda pop, you're drinking a lot of this phosphoric acid. Okay, that has 3 hydrogens, 1 phosphorus, and 4 oxygens. So a total of 8 atoms. The next one is called calcium hydroxide. Note the parentheses. That means in the parentheses, we have one of these polyatomic ions. And I know it to be hydroxide because I won the parentheses and then OH. Okay. And how do I know that? Because I've been staring at this screen for many years. If you look at OH right here, here's the polyatomic ion, got a negative charge, and its name is hydroxide. Okay. And therefore, that's why I know Ca is calcium. And that is calcium, is one of the 20 ions that you should be familiar with. it's calcium, and then in parentheses is calcium hydroxide, all right? And then we got Al, good old Al, AKA aluminum. And then we got another parentheses, oh, SO4. Now I'm giving you the names here because remember, we have a nomenclature exam. Nomenclature is nothing more than name that compound, either by formula, given the formula, given the formula, give the name, give it, you know, have the name, give the formula. And so, and that's why I'm introducing nomenclature and naming as we progress. So I look and see, I have a parentheses that sends me automatically to that table again. SO4 is in the parentheses. I look for SO4, and guess what? That is called sulfate. In fact, if you start looking, if you don't do that now, look at some of your food ingredients. You will find sulfate quite a bit. Sulfites, if you drink wine, for example, and you get like a terrible headache, you know, after a few sips, I don't mean like after a whole case, I'm talking after a few sips, it's probably, that's what happens to me. If I drink any wine, I start getting a little sip or two and I get a little headache because of what are called the sulfites. You read the label, it'll say sulfites. Some sulfites are vasoconstrictors and, you know, makes, I guess it squeezes the blood in your head and gives me a headache because of the sulfites. Anyway, we got sulfate that we're dealing with, so hence the name is aluminum sulfate. Note something else, something to pick up on here. I can mix and match. I can take the calcium and mix it up with the sulfate to have calcium sulfate, or I can get the aluminum and mix it up with hydroxide. Aluminum hydroxide. See how we start building a database of different compounds? Take the aluminum and cross it with, get hydroxide or the calcium with the sulfite, okay? Or then that table, there were multiple other polyatomic ions, negative, and I can take calcium, any one of those, mix it up, okay? And you start building a database of learning how to name the compounds. Name the compounds. And you probably, I would say the next 2-3 chapters, you probably have a good 1,000, 2,000 names that you can come up with, you know, not more. All right, so I was going to say for H2SPO4 or phosphoric acid, okay, we have 3 hydrogens, 1 phosphorus, 4 oxygens for a total of 8 atoms. The calcium hydroxide, the second example, we got 1 calcium. In the parentheses, there's a subscript 2, okay, telling us that we need 2 of these units, hydroxide units. If we don't need more than 1, we don't use parentheses, we just leave it as OH without the parentheses. But we have 2 oxygens there and 2 hydrogens for a total of 5 atoms. And for the last one, aluminum sulfate, we have 2 aluminums, there are 3 sulfurs in there, and there are 12 oxygens. And that is a total of 17 different atoms that make up that formula for their compounds, aluminum sulfate, that is. All right. With that information and knowing the atomic weights, okay, we can then determine what's called the composition, the law of definite compositions. And that means that by mass, that these elements to form the compound, they come in with a set amount of material. So water contains 11.2% hydrogen. Oxygen has 88.8% oxygen, okay? And that's true for water here in Arizona or true for water found in outer space, H2O. That is the composition, okay? Some of these percent calculations we're going to learn how to do later on. All right, so with that being said, congratulations. We are done with chapter 4. And we will continue with, well, you will continue with 5. So for next week, like I say, we won't be here next week. And we won't be here the following week, all right? So